everyone, and welcome to the Supercritical CO2 webinar. My name is Vince, and I've been using Flownex for many years now. I'm still surprised by the number of applications that the software has in so many different industries. Today, I'll be presenting a couple of models that I've developed in the Supercritical environment. I'd like to discuss three individual models. The first one is a steady-state model used for the design of optimal cycle efficiency. The next model will be a transient model where we look into some off-design performance analysis. And finally, I'll be looking into one of my favorite features in Flownex, which is a model incorporating multiple cycles and analyzing the effect of a change in one cycle on the system as a whole. Starting with the first cycle, over here, we have a heat recovery CO2 cycle. On the right-hand side over here, I have the outlet from a gas turbine, so 550 degrees Celsius. And then this heat is then used as the heat input to our heat recovery cycle in the center here. On the left-hand side, I simply have my heat rejection modeled as heat rejection into a water stream. This cycle over here consists of a compressor, a turbine sharing a common shaft, a recuperator, and then a couple of valves which I'll use to bypass the turbine. I'll discuss this a little bit later. Flownex includes quite a large number of components, particularly useful for building networks such as this. It has a huge library of heat exchangers and heat transfer components, a large number of turbo machinery components as well, where you can specify multiple different types of turbines with inputs based on the particular applications. There are also many fans and pumps that you can use for other applications as well. The components are defined in a manner which is consistent with industry. In this case, the compressor here is defined as pressure ratio versus corrected mass flow at lines of constant corrected speed. One of the particularly useful features in Flownex is that engineers are able to view the operating points of their components on the component maps. So in this case, I've defined the compressor as I showed you there, and we're able to view the operating points of the compressor on its compressor map. This is useful when analyzing surge margins or just generally when running transient analyses to see how the component is performing. We're also able to view a TS diagram of our cycle, which is updated live as the simulation is running. You can see exactly where the cycle is operating, and I understand that there are straight lines here. That's just simply how it's drawn. But it's usually good enough to give engineers a good feel for the performance of their cycle and just generally where it's operating. This particular model I'd like to use to illustrate an optimization of this recuperator itself. At the moment, the length of the recuperator is set to 8 meters. And what I'd like to do is vary the length of this recuperator to provide the highest output power from our turbine and compressor shaft here. As we increase the length of our recuperator, we'll see an increase in heat transfer, but also an increase in pressure drop inside this recuperator. And it's the balancing of these two that I'd like to analyze. To do this, we'll be using the parametric study feature inside Flownex. So what we have is an input variable. In this case, I've used the input of these pipes over here. I've specified a nominal, a low, and a high value, and then I've set the number of parametric runs as 20. Flownex then has an Excel reporting functionality, which I'm going to use to display the results. So if I run the sensitivity analysis, you'll see that each of these inputs here on the left-hand column are being sent to Flownex and applied to those pipes. The simulation is then solved in steady state, and the results are recorded in the column here on the right-hand side. There's also a graphing functionality inside the Excel component, as you can see, and we can quite easily see that there is a definite maximum for the system at about 15 or 16 meters in length. All right, I think that's it for this cycle. This can be applied in many different applications, and the parametric study tool can use as many input variables as you would like. I've simply displayed an example with one input variable, but we can quite easily extend that in whatever way you can imagine. Oh, one last thing. The pipe components here are displayed with or configured with increments. So this pipe has been discretized into 10 increments here, and we're able to view the increments, the results of each increment in this tab over here, I've displayed the temperature of each of the increments in the stream here. So we're able to view the temperature of each of the increments, but we can quite easily change this to another property. So for example, in a heat exchanger where you're looking to model two-phase boiling, you could visualize your two-phase convection coefficient and just do a sanity check on your model and make sure that your two-phase convection coefficient is increasing and decreasing as you would expect in the boiling regime. There are also three-dimensional increment plots which can be used to visualize more complex heat exchangers. For example, a fin tube heat exchanger where you visualize the temperature distribution in 2 dimensions or something similar to that. Right, moving on to the next network. It's exactly the same setup as before. However, in this case, I'm going to be running a transient simulation. So over here, what I'm going to be doing is simulating a turbine trip. At the moment, the shaft is configured to run at a constant speed of 3000 RPM, or 50 Hertz. During the simulation, I'm going to simulate the turbine trip by closing the inlet valve to the turbine, opening a bypass valve, and then setting the shaft to calculate its speed rather than fixing its speed at a constant value. What will happen is Flownex will calculate the power demand of the compressor, the power output of the turbine. Using that information, we'll calculate the net power on the shaft, which at the moment you see is 12.18 megawatts. And using this information, it will then calculate the acceleration of the shaft and a new speed of the shaft in the next time step. To display the results, I've decided to plot the shaft speed as a function of time, as well as the heat exchanger inlet temperature. So this particular analysis, I'd like to look at how the turbine trip is having an effect on our inlet temperature of our heat exchanger to ensure that the material itself is not going to be damaged during this type of event. So if I run the simulation, you'll see some of the results are already updating on the canvas here. You'll see for the first 10 seconds or so, the speed is kept constant. And then as soon as the option is set to have the speed calculated, you see the speed begins to drop. On the heat exchanger inlet temperature, we see quite a rapid increase due to the fact that energy is no longer being used up inside the turbine, or rather extracted inside the turbine. We're instead having this energy bypass through the bypass valve, and that higher energy here is just resulting in a much higher inlet temperature to our heat exchanger. You can see that there was quite a rapid jump from about 450 degrees Celsius to about 530 degrees Celsius, but it appears to be stabilizing, and it appears to be reaching a constant value of about 536. All right. This type of analysis is particularly useful for studying load change scenarios or trip events or startup scenarios or any type of transient event where your plant is operating in non-designed conditions. So it allows engineers to predict the plant's performance in these environments, and also allows engineers to kind of anticipate what could potentially go wrong in one of these events. The next cycle is particularly similar to this. However, I've coupled it to another cycle. So on the right-hand side over here, we have half of a Rankine cycle. I have a feed water pump, a feed water control valve, a steam generator, a steam control valve, a turbine, and then a deaeration tank. At the moment, I haven't modeled any of the other turbines in the turbine chain or the condenser, but this is sufficient for a demo, and it just keeps the model a little bit more simple. On the left-hand side here, we have a nuclear reactor component. I'll discuss this in a little bit more detail in a second. We have the nuclear reactor outlet connecting to a steam generator. In this case, I'm modeling a helical coil steam generator, and then a circulator, which just drives the flow of supercritical CO2 in this loop here. I've modeled the leak in this case, and this is the scenario that I'd like to investigate. In the nuclear environment, a loss of coolant accident is quite a severe concern and is often investigated. So in this case, I've put together a small demonstration network so we can analyze this particular event. What I've done is I've included a small little valve component, which I'll open at a particular time in the transient event, and then we'll begin to see some of the coolant leak out here. Soon after that, I'm going to have the reactor scram, so I'll have the control rods lower to their lowest position, and then I'll slowly begin to throttle down the turbine just to reduce the load on the secondary circuit as well. And we'll visualize the results in the network at the same time. The components over here at the moment are just controllers. They're acting as PID controllers, and their job is simply to control different elements inside the network. So the controller over here is controlling the control rod position based on the exit or the inlet temperature to our steam generator. The controller over here is controlling the circulator speed based on the pressure out of our steam generator. And the controller over here is controlling this feed water control valve to provide a certain outlet temperature. During the transient simulation, I'm going to deactivate this controller simply because I want to have the control rods drop to the lowest position, but this controller and this controller will remain active, and we'll be able to see the results of these controllers' actions during the transient event. As I mentioned, the nuclear reactor component is part of the components available in Flownex. So there's an entire nuclear section over here, and the nuclear reactor component is specified as follows. We have the reactor geometry specified in a 2D axial symmetric environment. So over here, we have inlet ports as well as flow channels, solid zones, and fuel zones modeled. And then we also specify the reactor neutronics. In this case, we specify the reactor neutronics parameters basically, and Flownex has a neutronics model which solves in parallel with the flow model. Basically, the temperature distribution inside the reactor is sent to the neutronics model, which then does a neutronics calculation and sends back a heat distribution map to the flow network, which is then solved. So it becomes a coupling between the two solvers, allowing you to analyze the reactor's performance in steady state as well as transient. All right, I'm going to start this network. We're able to see. So the network runs for a few seconds in its normal conditions, and then you see the control rods drop to their lowest position with the reactor scram. At this moment, the valve is open, and we have some of our primary coolant leaking out. I've put together a couple of graphs to try and illustrate what's happening at the moment. As you can see in the beginning, we have our reactor power here in purple, relatively stable in the beginning. And then as soon as the reactor is scrammed, we see an immediate drop in our neutronic power. This, however, doesn't drop to zero, as we still have decay heat inside the reactor. Part of the specifications on the neutronics chart included this, and are therefore accounted for inside this component. We see a slow drop in our reactor exit temperature due to the thermal inertia of the system, as well as all of that heat retention inside the solid zones inside the reactor. Over here, we're able to see our circulator speed as well as our main steam pressure. If you remember from earlier, there was a controller controlling the circulator speed as a function of this main steam pressure. As I mentioned, the turbine is going to be slowly throttling down during this process. At the moment, it's dropped from 85 to 60. I've set it to drop 1% every 2 seconds. So with that increase in resistance here, we're seeing an increase in pressure of our upstream turbine, or upstream of the turbine. So to account for this, we're having our circulator reduce its speed, and you can quite easily see that here in this graph. The next graph shows the steam flow, feed water flow, and main steam temperature. With the increase in resistance in our turbine due to the inlet nozzle closing, we see a reduction in our steam flow. To maintain the temperature at the outlet as best as possible, we're seeing our feed water flow decrease as well. And at the moment, it looks like the controller is performing slightly less ideally, with a temperature drop from around 530 degrees Celsius down to a temperature of about 430 degrees Celsius. So this is something that could be particularly concerning to an engineer in this environment and might be worth investigating further. The last graph I have over here is once again related to the nuclear reactor, and it shows the moderator temperature as well as the pebble temperature. So the reactor model over there was a pebble bed modular reactor or pebble bed reactor, and you can then see the pebble or the fuel temperature plotted here in red with the moderator temperature in blue. This functionality of coupling multiple cycles together can be extended in many ways in Flownex. So we're not limited to modeling simply power cycles here in the nuclear environment. You can quite easily model a cycle, for example, a solar cycle where you have molten salt storage. You'll be able to model a liquid salt loop or molten salt loop, as well as your solar collector with its heat input, and then a Rankine cycle downstream of that, for example. And you'd be able to analyze the performance of this cycle, or performance of the plant in general, over a large period of time to see how the changing molten salt temperatures would affect the performance in your Rankine cycle, for example. This is one of my favorite applications of Flownex, and I definitely believe it is an incredibly strong feature of this software. All right, that's everything that I have ready for today. If there are any questions, I'd be happy to answer them now. Otherwise, thank you very much for your attendance, and I hope you have a wonderful day.